Okay, we'll see how that goes.
And it's kind of
You're recording already, just so you know.
Well, it looks like you have a pretty good crowd.
Yeah, you know you have it recording already started.
Big one?
You have it already started recording.
Yes.
You want to do that 10 minutes before we start? We're going to be chatting.
Okay.
It's like 13
How
minutes.
come it disappeared?
You have to scroll your mouse down towards the bottom. Here, I can
Oh,
pause
there
it.
we go. Pause. I can pause. Here at Lehigh University, which is in Bethlehem, Pennsylvania. I know maybe different time zones from where you are tuning in, but welcome to the series of lectures. This is the fourth in the series this fall, and it's titled Managing the Grid with Increased Penetration of DERs, Distributed Energy Resources. So obviously a very topical subject, very relevant because most of the grid, especially the US grid, is still very much dependent upon rotating machinery to provide stability to the grid. So among other things, there are issues related to the grid stability as you increase DERs in the portfolio. So the abstract of the talk is the increase in DERs brings with it challenges in both modeling and parameterization of models used in transmission system impact studies. The speaker will talk about the challenges and the solutions that will be discussed, and he will be showcasing the impact of DERs on the bulk power system. And I'm very proud to announce the speaker is Deepak Ramasubramanian. He's a senior engineer scientist at the Electric Power Research Institute, EPRI, in the Grid Operations and Planning Group of the Power Delivery and Utilization sector. Deepak joined EPRI in 2017, where his work was in the area of modeling, control, and stability analysis of the bulk power system, with recent focus on the associated impacts of large-scale integration of converter interface generation. He received his Ph.D. degree in EE from the Arizona State University, Tempe, USA, and then in 2017, and his M.Tech degree in power systems from the Indian Institute of Technology, Delhi, in 2013. He's a recipient of an Energy Systems Integration Group Excellence Award, North American Synchro Phaser Initiative, NASP, Outstanding Graduate Student Award, and the Power System Operation Power System Award. And if I'm not mistaken, Deepak, lately you were a member of the NREL team, which was looking at grid forming inverters as opposed to grid following inverters. And so it's a real pleasure for me to introduce, to welcome Deepak to our seminar. Deepak, the floor is yours.
Yeah, thanks, Rudy. Just confirm once again that you can hear me.
Yes, we can hear you.
Awesome, great. Yeah, so thanks for that introduction. And yeah, so we do have a project ongoing, which is co-led by NREL and EPRI on grid forming inverters, and we are actively looking at how to manage more number of inverters on the system and try to identify what kinds of control techniques would be required for these future inverters. So in my talk today, I wouldn't cover that topic, but hey, probably it's a topic for a future seminar. So what I'm going to be covering on today is talking about this aspect about as we have more distributed energy resources, how do we manage the grid? What kind of parameterization of the models are required? And essentially what kind of impact we have on the system. Now, traditional flow of electricity has been a top-down approach wherein we have central station power plants pretty much generating megawatts or gigawatts of power, and then that flows through the network and ultimately in a fashion trickles down to each of our individual homes or buildings, university campus, industry, and so on. And that top-down flow of power has been the norm for close to 50 to 60 years. But that is changing now. It has been changing for the past decade or so, but it's becoming even more nowadays with respect to how we try to look at the operation of the network. And with more DER coming in, the change of flow on the network is now no longer top down, right? So you have, instead of you having just a load on the distribution side. So for example, your homes or maybe your university buildings may have solar panels on the roof. And what that essentially does is you no longer treat that house or the building as a load, but rather that building becomes a generation source also. And if you have a lot of such generation sources on the tail end of the network, which is what we call as distributed energy resources, then it can become a concern because the system is not designed to deal with that kind of change in flow of power. So how do we understand what kind of impact it has on the network? What kind of change in operational practice will be required? And in order to make those decisions, utility engineers need models. They need mathematical models in order to try to understand and plan the system. So we'll be talking about how we can model this kind of behavior, what are the challenges with modeling this kind of behavior, and so on. So now a lot of times, first thing to really try to understand when we talk about modeling is to understand why is it really important and what is the need for modeling the behavior of distributed energy resources explicitly. So what has been done or what has traditionally been done, say for the past 50 years is, and as you have small amounts of DER coming in, we wouldn't really worry about it initially, right? Because we would say, hey, there's say 2 megawatt of load being consumed by a building, and 2 megawatt is a lot for a building, but let's assume that 2 megawatt of load has been consumed by a building or a substation, right? So your local utility substation serves 2 megawatt of load. And we would say, hey, okay, so there's 2 megawatt of load and there's a couple of solar panels sprinkled on few rooftops, which reduces that load to maybe 1.8 megawatt instead of 2 megawatts, so 200 kilowatts of DER. And we wouldn't care too much about it, or that was the state of the art. But when the 200 kilowatt starts becoming close to say 1 megawatt, or it may become 1.5 megawatt, so it starts becoming a large fraction of the load, then it becomes important for the transmission planner to be able to study this, because if you assume that this is going to be the amount of DER at each bus on the network or at each substation, and you have a gigawatt size system, then what can start happening is DER have this behavior wherein the moment you have a fault occurring on the transmission network, and a lot of the legacy DER, so DER have started being in the network, as I said, for close to 15 years now, right? So in early 2000s and 2003, 2005 timeframe, a lot of the DER, the paradigm at that time was to say that, hey, if an event occurs on the transmission network, don't try to do anything, just trip and just immediately disconnect from the network, because firstly, the amount of DER at that time was small, but secondly, the aspect was not much was known about what the DER could do and what kind of services they could provide to the transmission system. So the thinking was that, hey, let this DER just trip so that we can take care of our system as we traditionally do. The challenge that comes up with that tripping of DER is when you're looking at a transmission network, you are thinking of, let's say, the entire eastern seaboard, right? So the entire eastern seaboard of US is one electrical network, so to speak. And it's not just the seaboard, it's just even stretches up towards the north. But just think of just the seaboard, eastern seaboard, and we don't model everything to the very last detail. Because if we model everything to the very last detail, then we would essentially take ages to run even one simulation study. So we can't afford to model all the load, all the pieces of equipment, everything to the very last detail. Instead, what we do is at certain voltage levels, we carry out aggregation. So traditionally, what is done in North America is we aggregate load at the 69 kV voltage level. And that is basically the distinction between, say, distribution system and subtransmission or transmission network. So anything below that voltage level is aggregated. Now, the reason why it becomes important now to model DER explicitly is a 69 kV substation may serve load of, say, 40 or 50 megawatts. And then you have multiple 69 kV substations in a vicinity, and that entire region may be serving a load of, let's say, 500 or 600 megawatts. Now, DER in such aggregate amounts, if they start tripping, because of how we said that we wanted the DER to trip and we want to restore our system or let the ride through the fault in the traditional way. Now, if DER of such large amounts start tripping, and they can start tripping in this block fashion, wherein you would have for very small changes in voltage level, you can have very large changes in amount of DER that trip. Now, if that starts occurring, then it can cause a very large disturbance on the transmission side. And we need to get that visibility in order to ensure that if there is an event on the transmission network, which we have not planned for, and this kind of block tripping is going to occur, then we need to be able to see that event occurring and we need to be able to plan for it. So that is the reason why we want DER to be modeled explicitly. Now, when I say explicitly here, it doesn't mean that we model every single rooftop. There's still an aggregation that's going to happen, but we need to be smart about the way we carry out that aggregation so that we can get a visibility of the kind of behavior that we expect from DER. So the model that we need to construct has to be smart, or we need to construct the model in a smart manner so that we can really capture the behavior of DER as we expect it to occur in the system. The challenges that occur with the development of this model is that transmission power system analysis is pretty much carried out in what is known as positive sequence environment. So all our analysis that we do on the transmission system, we carry it out in positive sequence, wherein we essentially assume that all three phases are represented as a single phase, which means that we assume that voltage and current are balanced. What we also assume is that the dynamics of the transmission network, so the lines, the capacitors, the inductors, and everything that's there on the transmission network, we assume that those dynamics have reached a steady state. So essentially, we do not use differential equations, we use algebraic equations to represent the dynamics of the transmission network. And finally, what we essentially assume is that the amount of harmonic content in the transmission network is low for the kind of disturbances that we want to study. So because we make that assumption, we can say that we are going to represent the inductors and the capacitors as their fundamental frequency component. So you might have come across in basic circuit theory that the impedance of an inductor can be represented as omega nominal times L, and the reactance of a capacitor is the inverse of omega nominal times C. We assume that the omega nominal is fixed constant value, and we represent that value as an algebraic value. So we make these three assumptions when we do transmission analysis. And these three assumptions are based on some legacy insight and so on that has been carried out for quite a few years. And this gives us the ability to actually really do computationally efficient simulation studies. Now, why this becomes a challenge with DER is that DER essentially, they can trip on single phase voltage. Now, even a three-phase DER, if it has three phases of voltage, but it can still trip if there is only a single phase event or a single phase voltage that occurs. And a lot of times the fault which occurs on a transmission network will propagate through various transformer configurations and transformer winding configurations. They would propagate down to the distribution network in various forms, which cause a variety of DER tripping mechanisms that can occur. So now, since to begin with, we started saying that one of the main goals of capturing this DER behavior is to get an understanding of how the DER would trip if a transmission event occurs. But if the transmission or if the tripping of the DER is going to be influenced by the phase distribution, if it's going to be influenced by the transformer winding configuration, if it's going to be influenced by the type of fault that is applied, then one asks the question that, oh, hey, all these assumptions that we have made in the way we represent our simulation studies, this balanced phases, the fundamental frequency component, and so on, would that be a hindrance to providing a good visibility of how these DER would behave? And that is the challenge that we want to try to address when we create our DER models. So what we essentially use to represent the dynamic behavior of DER and load is this model, which is called as the composite load model. And what this composite load model has is, as I mentioned before, it's still an aggregation of the dynamic behavior of the various equipment that we have on the system or on the load side. So we have a combination of motors that can capture the dynamic behavior of loads like pumping load or air conditioners and so on. We also have components of DER that are represented as these RDER components and the UDER components. And they essentially represent few different types of distributed energy resources on the system. And I'm happy to provide links to those who are interested in learning more about these different types of DER. Now, with any model, we ask ourselves these questions: that is this representation perfectly accurate? And we can immediately say that no, it's not perfectly accurate, because we are representing the behavior of an entire network which might have so many different elements in it. We are representing that purely by by a aggregated representation or a simplified representation. So it's not necessarily going to be accurate. But does the representation need to be perfectly accurate is a second question that we want to ask. So one thing is it's not accurate, but do we really need that level of accuracy? And the answer most of the time here is that we don't need the perfectly accurate representation, because what we really need is that we need to get a representation of the dynamic behavior that enables transmission planners to carry out their studies and to make decisions based upon the studies. So if the type of decision that they create or the type of decision that they come upon is not going to change whether they use a detailed model or whether they use an aggregated model, then the detailed model is not really required and the aggregated model is sufficient. So that's the ideology and thought process behind creating this model. But even though we have created the model, there is still a challenge in how do you represent the behavior of DER itself. So the challenge is essentially, as we said, that we have this entire network that needs to be represented. So you have, this is just one distribution feeder. Many a time the same substation will feed multiple distribution feeders. So this one feeder or the multiple feeders has to essentially be condensed down into a representation as we showed before. And furthermore, what needs to happen is this variety of distribution of voltage that we see across the network or across this feeder essentially has to come down to a representation like this, because you have your three-phase voltage profile has to be represented by a single-phase RMS equivalent, because that's how we have transformed the entire model. Now, the impact of this, or the challenge of representing the variety of load, the motor load, the impact of the motor load, and so on, is a separate topic, which we won't cover today. There's a lot of work that goes on how do we get accurate load model representation and sufficient load model representation. What we'll cover today is this topic of the DER. So what we have done in being able to represent this DER is we have created a model which can essentially represent the aggregated behavior of variety of DER. And it does this by being able to capture the performance of a variety of DER based upon the kind of services and properties that they would provide. So you have a section of the model that can provide frequency control. You could have a section of the model that can provide power factor control, voltage control, and so on. There's a reference here that you can refer to learn more about each of these types of sections of control that the DER model provides. Also, what it has is, and what's the most crucial part of this model is it has the ability to represent partial tripping of DER across the network. Now, why this partial tripping is important is, as we saw in this slide, right? So you have a spread of voltage across the entire network. And essentially what you have is you have the substation voltage here. And as you go deeper into the network, you have a spread of voltage in this manner. Now, rooftop PV or any kind of inverter-based resource, which is a DER, is essentially a power electronics device that can operate or trip based upon a measured value of voltage. So if it sees the voltage below 0.9 per unit, or if it sees the voltage below 0.8 per unit, then that device may trip, or it may go into a type of operating mode that may not be adequate, or it may not be good for the system. Now, if you have this kind of voltage spread and this voltage profile across the network, wherein you have certain locations which may see a voltage of 0.95 versus certain locations which may see a voltage of 0.93 or so on, and certain locations which may see a voltage of 0.98. And the values that I'm mentioning may not really line up with the scale, but you can just scale it up and down to understand, because this is a steady state voltage plot. The values that I'm talking about are based upon events that occur. But the same methodology holds that if you have, say here, you have the substation voltage as 1.05, and you have voltage going down all the way to 0.95. So you can have certain sections of the feeder seeing a higher voltage as opposed to certain sections of the feeder. So now if an event occurs, you might have a scenario where, say, half the voltage. So let's just take this particular profile here, wherein a majority of the nodes have voltage which is greater than 1, but you have nodes also that have voltage which is less than 1. So this is the one per unit voltage point. Now, if you had a DER that is going to trip at a voltage of, say, 1 per unit, so DER don't trip at 1 per unit, they trip at 0.9 or 0.8 kind of voltage level. But given that we have this plot of voltage here, let's assume that they trip at 1 per unit, then what will essentially happen on this feeder is that any DER which is located at a node which has voltage greater than 1 per unit will not trip, and any DER which is located at a node which has a voltage less than 1 per unit will trip. So in an aggregated fashion, when you have an aggregated model such as this, wherein the entire DER is placed as one model, and all it's going to see on the entire model is going to see only one voltage, which is at this bus, we need to have a mechanism of being able to capture this fact that certain percentage of the DER may trip and certain percentage of the DER may not trip. And that is what these blocks do in the model. And again, there's more description on it in this reference. We have essentially done work to find out that how could you represent this partial tripping? How could you represent this fractional tripping of DER across an entire feeder and still incorporate it within one model itself so that you don't have to have a very detailed representation? So these are the insights, and these are the kind of techniques that we use in order to develop these models, or these are the points that we need to keep in mind while developing the models. But developing the model is only one part of the entire problem. But just by developing the model, we don't really get the solution that we need or get the solution that we want to achieve, because an integral part is how do we apply parameters into the model. So for example, you might have the most detailed model that you want, but if the parameter values that you put into that model are not correct. So a model at the end of the day is just a set of equations. But if you don't apply the correct values of parameters into those equations, then you cannot expect to get a good response from the model. So when we look at models, we have to always understand that even if you have the most detailed model, it will still have some limitations, because there's only so much you can do to represent a behavior by mathematical equations, and there will always be some form of limitation that comes up from the mathematical model. Some of these models are useful, but they're only useful if you apply or if you parameterize the model with an appropriate set of parameter values. So the challenge that comes up with parameterization now is we have created this aggregated model, but how do we really create parameters for that aggregated model? So if you go back to this example that we had, wherein you can have DER tripping at different values of voltage. So what's essentially done here is you have faults applied or events applied on the transmission network, where the voltage during the fault goes down to these values. So if for the blue curve, the voltage during the fault is 0.94 per unit, 0.93 per unit for the orange, 0.92 per unit for the green, and so on. And this plot shows how DER behave in aggregate. So you have the fault being applied here. When the fault is applied, you have the active power output reducing, and then the fault clears. And then you have this wide range of response of the DER. So this fault has cleared. What has essentially happened here for the brown curve is that almost all the DER have tripped. Whereas for the blue curve, all the DER were able to recover and ride through the fault. So now if we take these endpoints, right? So if we take this value of the active power that has remained after the fault has gone past, and if we just take these endpoints and plot them against the voltage level, we get a curve like this. So one can say that, oh, okay, this is reasonable enough of a linear trend. We can fit a linear line to this curve, and we can get our response, or we can get our tripping behavior. But where it becomes complicated is that this kind of linear trend holds for this topology of DER. Now, if I mix the topology, so now why I'm saying we're mixing the topology is if I sit on the transmission level and I'm aggregating devices at the 69 kV voltage level, that essentially means that I don't have information, or I may not have information about the network that is lower voltage than 69 kV. And if I don't have that information, that means that there's so much of uncertainty that I have to cater to. Now, one of the aspects of information that I don't have is I don't know exactly where DER are located. So DER could be located anywhere on the feeder, and I don't have that information about it. So now what's shown here is if I create a set of runs which basically randomizes the location of DER on the feeder, then I can get a very different set of tripping that can occur. For example, here, if I have one set of locations of DER, 60% of the DER are able to ride through for this event. But if I change the locations of DER all the time keeping the same amount of total DER that is coming out from the feeder, then 100% can also ride through. So now fitting a linear trend for this can become difficult. So we have done some statistical analysis and try to find out that, hey, okay, what is the best way in which we can really fit the data and how we can really generate the parameters and so on. It's by no means a process that is complete. It's by no means a process that cannot be improved. There are always ways to improve the performance. but it's a way we have generated so far. And there are papers that I can refer you to if there's interest. But what we essentially try to do when we have this parameterization process is we want to try to minimize the impact of uncertainty on the transmission planner. The transmission planner already has minimal to zero information regarding these factors. And these are all factors that can impact the way DER trips. What we want to try to do is minimize this uncertainty by essentially having some rules or by having some generic values that can help understand what the way of tripping of DER would be. So the process that we have developed to really set up these model parameters is we try to have an as straightforward process as possible. And we essentially say, okay, the starting point should be the relevant IEEE standard. Now, in most portions of North America, the relevant IEEE standard is IEEE standard 1547. So most of the model parameters can be obtained using this standard. So once we have the standard set up, then we work with a lot of distribution companies and a lot of distribution entities to really identify that, okay, if they have access to data, if they have access to their detailed distribution analysis procedures and simulation environments, then we can essentially create a set of probabilistic and stochastic runs that will ensure or try to evaluate that as you have different locations of DER, and that's essentially these two steps here, that as you have different locations of DER on the feeder, how the tripping characteristic of the DER changes, what kind of tripping behavior would be observed, and really how we can use that to derive the aggregated model. And then we can work across multiple types of feeders. So then a question comes up, okay, what if you don't have that information? So this process works if you have the information available, but what if you don't have the information? So that's where from EPRI side, we do a lot of work on the back end to really carry out this process for the types of feeders that we have, and then try to understand what may be the similarities between different types of feeders, what are the differences between different types of feeders, and how can we use them to generalize the results that we obtain. And we've had some success with that. One of the examples that we tried out is we tried it out using a feeder in Arizona. So the feeder is purely urban residential. It has a slight amount of imbalance in load. It has a variety of distributed energy resources also located, and it also has a voltage profile that spreads out a little bit during peak load conditions. So since it's primarily residential, we assume that, okay, hey, this only single phase DERs that will be there in this feeder, there would be no three phase DERs. And we also assumed that if there is only single phase DERs put in, we would assume that each home would add a rooftop PV whose rating is around 50% of their peak load. So that brought up the total amount of DER to be 50% of the peak load during peak loading condition, and 282% of the peak load of the load during minimum load condition. So we added a massive amount of DER on the feeder in order to see how the system or how the aggregated model would set up. And we also had, because we were doing this detailed analysis, we also had to look at what is the voltage profile across the network, both with and without DER, and we see what kind of behavior we get. Now, one thing to note here is that since this setup or this kind of study was done a few years back, it's essentially assumed that you don't have any smart features in the DER, because smart DER, especially from the perspective of transient timeframes, those DER have only started coming up in the network in the past 1 or 2 years. So when this analysis was carried out, we essentially assumed that these DER do not have any smart features enabled in them. So as we did a large amount of studies and we did a evaluation of the tripping profile of the DER, we were able to then generalize and find out how we could really obtain that trip characteristic of the DER_A model. This results here on the left essentially show how we would, the kind of procedure that we used to set up the trip characteristic of the entire DERA model, and we carried out some amount of statistical analysis to obtain the exact values that we would have to put in for these DER. So we then use that to determine the generalization approach. And what we essentially say is that the first inverter to trip on a system is likely to be located towards the tail end of the DER, because that is where you have the largest voltage drop most times. And the last inverter to trip was likely to be located towards the head of the feeder. It's all kind of intuitive when you look at it. And the first inverter would trip when the voltage is, say, below the trip threshold. In our case, it was 0.88 per unit at the tail end. And the last inverter would trip when the voltage is below the threshold at the head of the feeder. Now we can essentially translate that to a positive sequence by assuming that the bus at which the DERA is located is the tail end of the feeder. It's still a big assumption, but so far it has helped us in our analysis. And if we assume the net downward trend of voltage, then we can utilize some heuristics or rules of thumb, especially with respect to how much there's the drop of voltage across the feeder, to really set up the parameter values of the DERA model to generate the tripping profile that we want to see. And we can then change that based upon the standard. So as I said, a lot of the characteristics can come up based upon the standard that we use as the baseline. So depending upon whether we use the default IEEE 1547 standard, or we use something called California Rule 21, which is applied in California, or we use some of the newer versions of the IEEE 1547 standard, we can then generate rules of thumb to parameterize the aggregated model so that we can get the performance of DER that we expect. And if we do that, then we can get this result like this, wherein what's shown in the blue stars are the performance of the detailed distribution analysis to really identify what kind of tripping would occur. What's shown as the black dots are the analysis from the aggregated models to try to showcase how the tripping would set up or how the kind of tripping behavior would be observed. So it's, again, not perfect, but it enables a transmission planner to make the set of decisions that they would have to carry out and gives them a visibility into what kind of behavior they expect to see. Now, all of this lays down the process for parameterization. But as I said at the beginning of the section, that the use of a model or the kind of inference that one gets from a dynamic model is only as important or only as valuable as the parameter values that we put into it. So one has to be really careful when parameterizing these models, because ultimately at the end of the day, the model might give a result, and that result might be in line with the values of parameters that have been put in. But if the values of parameters themselves are unrealistic, then the results can be expected to be unrealistic. So if we take two examples of looking at importance of parameterization, so take this first example where the DERA or the aggregated representation of DER was applied to a very large area in the eastern portion of the North American power system. So if we apply this aggregated DER representation to this large area, and it was so large that that entire area was represented, wherein there was around 3 gigawatt of aggregated DER that was forecasted to come into a certain area of the system. And the non-DER generation is around 8 gigawatt available in the network. So there's a total load of around 12 gigawatt in that region, wherein out of that 12 gigawatt, there's 3 gigawatt of DER based generation coming from the distribution network into the entire system. So what was done is that we assumed these parameters, and we essentially say that all the DER trips if the voltage stays below 0.89 per unit for a time greater than 2 seconds, and all the DER would trip if the voltage stays above 1.2 per unit for a time greater than 2 seconds. So, and all of these individual variable names are there in the previous references on the slides regarding the model, and they specify what these variables relate to. Now, the simulation study that was done was trying to identify that if this area isolates from the rest of the system, then will that area survive or not? And what will happen to the DER in that area, and what will essentially happen to the system? Now, this kind of a area separation study is actually required to be carried out in certain regions of the network to understand the reliability risks and understanding the security of electric supply for that portion of the network. So the study itself, or the scenario itself that was being studied, is not an unrealistic scenario to study, because it's part of the planning criteria that needs to be carried out or ascertained. So what you see is that if you have a scenario wherein you have, and this is just to verify or the robustness of the model first. So we don't even have, this is not yet wherein where you isolate the entire area. This is just to show that, okay, even if you have so much of DER in aggregate, then you can ensure that the DER model, or the aggregated representation of DER, provides the kind of results that you may expect, because for certain scenarios it is fine. But if you have a fault and then you trip the event, then what essentially happens is that you see a lot of DER tripping. Now, the question that needs to be asked here is that, is this tripping because, so if a transmission planner is running this simulation, right? The first question that may come up in their mind is, hey, this model is not showing us the behavior that we expect. So which means that the model must be wrong. But a lot of times what essentially happens is that the model is providing the behavior as expected in terms of the parameters that have been provided to the model. So it's not that the model is wrong. It's more about the fact that the parameters in the model are probably unrealistic. So in this particular example, if you have a 3 gigawatt of DER generation and you have a fault which causes the voltage to go quite low for an extended period of time, then all the DER trip and you have 3 gigawatt of loss of generation. And since the system is separating, you essentially do not have enough headroom or energy reserves to ride through that loss of disturbance or loss of generation, which then results in the entire model or in the entire simulation crashing. So here in this case, it's not that the model has a wrong response or a wrong result. It's more about the fact that the parameters that have been put into the model showcase this response, and that needs to be looked into. So this is just to show that a lot of times when one sees a response in a simulation study, which looks like this, one has to immediately think about not just whether the model is correct or robust, but also whether the parameters that we have put into the model are correct. So one more example on that is, we talked about transformer configurations in the earlier slides, right? As to how, when you have a single phase fault, that depending upon whether you have a star winding or a delta winding on the transformer, that single phase fault could be represented in multiple different ways across the network. So can we have this fundamental frequency transmission system positive sequence representation? Can it be used to represent the behavior of this DER tripping in this fashion, is something that we wanted to see. So if we just understand the concept behind how this transformer winding impacts the way in which faults will be propagated. So we have here a delta star winding and you have a star star winding, and we would apply the fault here on bus 1, and we want to see how it propagates down to the DER here. So a lot of you might have derived these kind of sequence network diagrams in power systems classes, wherein you can try to understand that if you have a star-star connected transformer versus you have a delta-star connected transformer, you essentially have a change in the zero sequence network and in the structure of the zero sequence network. and it also results in changes in the angle in the positive and the negative sequence network. So because of these differences in the transformer winding configuration, you can then really get an understanding of how DER would trip. So here in this example, when you have the transformer being star-star connected, the fault on one phase on the transmission network impacts only one phase at the feather distribution end. Whereas when the transformer is delta star connected, the fault on one phase on the transmission network impacts two phases on the distribution network, but the impact on each phase is not as drastic as the impact on that phase when the transformer was star-star connected. So we can utilize this kind of information to derive rules of thumb and approximations with respect to how DER would behave for these transformer configurations. And we can essentially try to assume that if we make an assumption of the percentage of spread of DER across various phases, we can make a determination of how much DER would trip, what kind of voltage level should we derive, and so on. And we have done that to essentially come about with trying to understand how to parameterize these aggregated models for unbalanced behavior or unbalanced faults. And here is the same kind of example as we had seen before, wherein when you have detailed distribution simulation results being compared against an aggregated behavior, essentially showcasing that the aggregated model could represent the behavior for unbalanced faults. Now, where this becomes important is for a transmission system study, single phase faults are much more common than three-phase faults on our network. And that's thankfully so, because three-phase faults can be very drastic. But if single phase faults are much more common on our network, then if you consider two examples wherein you have the system and it's a transmission network, which has close to around 69 gigawatt of generation, has around 81 gigawatt of load. So we have a total of 14 gigawatt of DER. And of course, this is spread out over a large area, right? So you have an entire large network of this. Now, if you consider two scenarios, wherein for transmission line A, we apply a single line to ground fault, then in the scenario where everything is represented with the same fault, if it is a three-phase fault instead of a single line to ground fault, then you would see the blue curve, wherein you would have an approximate amount of 200 megawatt of DER tripping. Now, if you apply that same fault as a single line to ground fault, but if you don't consider transformer winding configurations, if you don't consider the impact of this different kinds of winding configurations on tripping and so on, then your simulation might still tell you that only around 200 megawatt of DER would trip. But actually, if you consider those impacts of different amount of winding configurations and so on, there's actually close to 700 megawatts of DER that could trip. Now, if you look at it on the other side, if you look at a different transmission line event, then you can even have a scenario that if you don't consider winding configurations, you might actually see a result in a simulation that says that no DER would trip, whereas in reality, around 800 megawatt of DER trips. So where this becomes important is to showcase that the kind of parameterization that we apply into our models needs to really be thought about carefully, because it can change the way we get our results. And these changing results can really impact the type of decisions that we make as transmission planners. And it becomes even more important here because we are not representing all the elements of the network, because we cannot computationally represent all the elements in the network. We have to make approximations. We have to make aggregations so that we can run our planning studies and our operational studies in a very short time frame, so that we get timely decisions. So when we make such kinds of assumptions, or when we need to make such assumptions, it becomes even more important that we really pay attention to how we parameterize our models. So just to close out, we've seen that from a transmission system side, because we needed to make these assumptions, because we don't have visibility into a lot of details on the distribution network, we have to be extra careful on how we parameterize our models. We need to be extra careful on how we develop our models itself in order to represent this aggregated behavior or this aggregated impact. we have had some success across the industry, which is with this DER_A model, which has shown to be robust. But it's also possible that because of the nature of DER, it's also possible to have a large amount of DER tripping for certain events. That doesn't necessarily mean that the model or the parameterization is wrong. One needs to really understand the cause of such large amounts of tripping that can occur and work with that kind of understanding and notion. So when we see simulation results that cause a lot of tripping on the system, the initial knee-jerk reaction shouldn't be that, hey, the model is wrong, or hey, the simulation software is not correct. One really needs to understand the cause behind that tripping, because with DER, it might actually happen, and that's the challenge that we face. Some of the open questions that we still have is we really need to understand if there is a way to represent the loading conditions. So if you have different seasons, how will the trip parameters change? How will the aggregated representation change? What kind of extension can we make to different types of feeders? So we've looked at urban residential. Will it be different for rural residential? Will it be different for commercial feeders? Will it be different for agricultural feeders, and so on? That's the kind of research work that we still have to carry out. Uh, Unbalanced faults is always tricky because there can be so many combinations. So really trying to identify how many combinations can be represented by this aggregated model is something that we are still working on. And finally, where are the limits? So after a certain point, we do have to say that, hey, it's not worth it, or it's not possible to continue using this kind of an aggregated representation, whereas maybe we need to explore different kind of computational techniques, different kind of simulation methods in order to really represent the behavior of these distribution devices, which might mean co-simulation of different simulation environments together. So those are the questions that we're still working on and looking to address. And with that, that's all I had for this presentation.
Well, thanks a lot, Deepak. And as we normally do at such seminars, I'd like to open the floor first to the students here. And so students, if you have a question, please unmute yourself, introduce yourself and ask the question. And I'm sure Deepak will entertain that. And then we'll move on to the general audience. I just want to acknowledge there's a number of utility attendees. So welcome again, to the seminar. And obviously I'd love to hear your thoughts and comments and questions for Deepak. So anyway, students, have any questions? Please unmute yourself and ask a question. Students? So while they're still thinking, Deepak, a general question for you. Does this model and parameterization that you developed, is it blind to what is behind the meter or rooftop assets, or is that not the case, or is the question just not right?
It's not blind to that, because essentially what it does is it's trying to represent the combined behavior of each of these assets. Now, where the power of the aggregated model really comes into play is if you have a large amount of this DER on a feeder. So if you have only one or two installations, so to speak, then it's probably not worth it representing the entire aggregated behavior. At the same time, what it does have a limitation with respect to is it cannot represent the individual characteristics of each DER, because it is representing, at the end of the day, what we have as an aggregated response, as you see at the substation level. But we have done a couple of studies wherein if all the DER is rooftop, then the aggregated model can still represent the behavior that we see.
Okay. A couple of questions in the chat box from Oshan. I'll just read it verbatim. Your argument or why we do not perfect accurate representation is because you're getting similar results when you simulate detailed models versus aggregated models. Can you clarify that?
Yeah, so why we don't chase perfection is because every model has a limitation, right? And if we start chasing perfection in order to get a perfect and accurate result, then either the model becomes very complicated, or we have to have a tremendous amount of data in order to get that perfect result, or we need to have, essentially everybody needs to have a supercomputer in order to really churn out those results. So that is why we don't chase perfect accuracy. What we do chase is we want to get a realistic representation of the behavior that we expect to see. And the realistic representation is sufficient if, so supposing I'm a transmission planner and I'm running a study, and I want to understand if I need to say, I have, let's say, 100 megawatts of DER coming in, and I do a detailed study with detailed models. And let's say the conclusion that I make from that detailed study is that, yeah, I have to add a transmission line to a certain portion of the network in order to improve the response of the network. So I did that detailed study. I spent, let's say, 50 hours doing that detailed study. But say I use an aggregated model, I spend 2 hours using the aggregated model. I don't get the exact same results, but I still walk away with the conclusion that I have to add a transmission line to this section of the network in order to improve stability of the system or reliability of the system. So my net conclusion has remained the same. The inferences that I have got has remained the same, but rather than spending 50 hours doing a study, I've spent only 2 hours doing a study. So that is what we are trying to chase with the aggregated model, that how realistic can the results be, and how do we ensure that the results continue to remain realistic enough so that the decision-making process and the results that we get from that study remain the same, whether you use an aggregated model or the detailed model.
Okay. Just related to that, there's a question from Oshan again. Let me read that. Can we use your DER models to study the behavior of similar aggregated DER applications such as virtual power plants?
Yep, yeah, we absolutely can.
Okay. This could be of a lot of interest to utilities in the audience. Let's see, any questions from students? I'd like to open the floor to others who want to ask a question. Please unmute yourself, introduce yourself. Questions from the general audience? More questions in the chat box. Let me see. Okay, from David Ellis. David, do you want me to read the question or you want to ask the question?
I'm good either way, Rudy.
Okay, go ahead. Ask your question, please, David.
Okay. The subject of ride-through programmed into inverters so that they can hopefully not be as sensitive to transmission line faults has come up. And concerns have been raised that some utilities are doing live line maintenance on 4 and 13 kV connections. And there's been a great deal of concern that utilizing ride-through settings on inverters could subject utility workers to greater hazards than using old-fashioned trip settings on inverters. And I'm just wondering if you're aware of any work that's been conducted to try to quantify or address that question of what exposure might be present.
Thanks, Dave, for the question. Really important. Personally, myself, I am not aware of that because I have not been involved in the discussions that changed the write-through settings, because I only know that the settings changed and then we adapt our models for that. But what I can definitely do is there are other folks at EPRI who have been involved in those discussions regarding why should the write-through settings change and what are the impacts and what are the considerations involved in changing those write-through settings. And I can get in touch with them and try to find out if they have this information that you're asking for.
Thank you very much.
A related question from Kala Rashid with Exelon. What application software was utilized to create this model? Was it MATLAB, Python?
Yeah, so the model itself is actually available now in all commercial power system simulation software that are used by transmission planners. So there's software by GE called PSLF. There's a software from Siemens called PSSE, and so on. So the model itself is available now in all those power system simulation software. For the detailed distribution studies that we did, we used OpenDSS to carry out the studies.
Okay, we're still open for questions on the chat line, or if you want to ask it orally, please unmute yourself and ask a question, please. Questions for Deepak? Deepak, is there any reason to believe that this approximation would degrade with increase in penetration of DERs, or that's not true?
There definitely can be degradation, but it's also two things to think about there. That it can be degradation with respect to the present status of the model, and then that would mean that we need to have an improved model itself. So we have to improve the aggregated model further in order to take care of the performance that we see with the increase in DER. And if there is, like, after a certain point, that there may not be an improvement possible, or the improvement may not really give us the kind of additional inferences that we want, then we would have to go to techniques like co-simulation, where we simulate one portion of the network at a higher level of detail, but we simulate the portions of the network that have the DER at a greater level of detail. So I think what we have seen is that sometimes if you have a very high percentage of DER with let's say a lot of induction motors and things like that, and if you're studying events where the fault occurs near the substation, then the aggregated model may not provide the best result, and one needs to do a detailed study.
Good. Any other questions for Deepak? Questions either in the chat box. If you want to enter the question, please go ahead, or ask orally, please. Okay. So our next seminar is 3 weeks from today, on 24th of October. The speaker is Revis James, a former EPRI employee, and he will be talking about the electric power system and policy. You know, as technologists, as many of us are technologists, we forget sometimes that to remember that policy is a bigger driver than technology itself, and our policies in the United States are run by states, and each state could have a different policy, although there may be some overarching federal policy. And Revis is going to give us a snapshot of what is it that would drive new technology and what kind of policies would need to be in place. Anyway, thank you for your attention. Thank you for your attendance. And we look forward to you at our next seminar, October 24th. Thanks a lot, everybody. Thank you, Deepak.
Thank you, Rudy. See you.